I have an example here already. I've run this example from the NES 2012 data set. This shows the sample mean of a feeling thermometer variable. It's the FTGR_gay feeling thermometer, that is to say respondents' ratings of gays and lesbians. Overall, respondents rated this group at 51.63. You know that the feeling thermometers range from 0 to 100. So we can say that the true population mean is equal to 51.63, give or take a certain amount of random sampling error. How big is that error? This statistic, the standard error of the mean, this tells us the amount of random noise that's contained in our sample estimate of 51.63. In fact, it is an established statistical rule that 95% of all possible population means are going to lie between 51.63 minus 1.96 times the standard error, which in this case is 0.377 at the low end, and 51.63 plus 1.96 standard errors at the high end. I've done an analysis here, which we will repeat in a minute, that has returned those values. 95% confidence interval. There's a 95% probability that the true population mean lies between 50.89 at the low end and 52.37 at the high end. Now, what does this mean from a practical standpoint? This means that any hypothetical claim about the population mean that lies in that bandwidth is plausible. We will not reject it. Why? Because there's a probability of greater than 0.05 that it's correct. For example, suppose someone looks at our sample mean, 51.63, and says, well, you know, I think the true population mean is really 52, not 51.63. We wouldn't reject that claim because we can tell from just the confidence interval alone there's a probability of greater than 0.05 that the true population mean is 52. Now, to say that 52 lies within the 95% confidence interval is logically the same as saying that the difference between the observed sample mean, 51.63, and the hypothetical claim, 52, is not statistically significant. Or in other words, there's a probability of greater than 0.05 that the difference is equal to 0. Ordinarily, we don't calculate 95% CIs and then see if a hypothetical claim lies in that interval. We calculate the difference between the observed sample mean and the hypothetical mean, and then calculate the probability that the difference between the two is greater than 0. Let's perform that analysis. In fact, let's go here to analyze. We're going to go down to compare means here. Go over to one sample t-test. Here's the analysis I performed earlier. I just simply ran it on its defaults, but FTGR_gay, and I just left the test value at 0 to obtain the results we just discussed. Let's replace the test value here with the hypothetical claim, 52. And let's find out the 95% confidence interval of the difference between these two means, and let's also find out the probability value that the difference between them is 0. Here are the results. One sample statistics, you can see here's some repetition. There's the sample mean, 51.63, and the standard error. Here's some new added information. Here's the test value that we entered, 52. What SPSS did was it took the observed sample mean, subtracted from it the hypothetical mean, 52, and recorded the difference here, minus 0.373. It then applied the 1.96 rule and calculated a lower and upper confidence boundary of this difference. SPSS tells us that we observe a difference of minus 0.373, but taking random sampling error into account, the true difference could be minus 1.11, or it could be a positive number, 0.37. Notice that 0 falls within this boundary, the confidence interval, the difference. We knew that it would, since we can still see the results up here. that 52 falls within the 95% confidence interval of the sample mean. So the difference between them must contain 0, and certainly it does. So we know from this that the probability that the two means, the hypothetical and the observed, were drawn from the same population of means is greater than 0.05. Exactly how much greater than 0.05? This is where we can get more precision by running the analysis this way, as we just did. Over here, SPSS has calculated a t-statistic, minus 989, and more importantly, an associated p-value or probability value, 0.323. How does one interpret this number? Like this. There is a probability of 0.323 that the sample mean and the hypothetical mean were drawn from the same distribution of means. It's more proper and technically more correct to say this, to interpret it this way. If the difference between the two means is assumed to be 0, then random sampling error would produce the observed difference 32.3% of the time by chance. So the assumption that the difference is 0 really stands up, since there's a 1/3 of the time we'll get a difference that we observe here. So the no difference hypothesis holds up. From the 95% CI up here and also down here, the CI of the difference, we knew that the probability was greater than 0.05. Now we have a much more precise calculation for that, 0.323.